The universe has a non-renewable resource few think about. It's the ultimate non-renewable. Once it's depleted, everything's over. The stars, every single world, all gone.
The sun, the galaxies and planets all collapse into black holes and then evaporate into radiation, so that the entire universe is filled with radiation, and then nothing more can happen. There'll be no life possible. No other extraterrestrial civilizations will be possible.
To get a feel for this non-renewable resource, you need to understand the concept entropy. Entropy is a measure of how disordered things are. So, in a perfectly ordered deck of cards, the entropy is very low. But if I take the pack and shuffle it, as it becomes less ordered, its entropy is increasing. Now, entropy is at a maximum. Or, think of it this way. There's nothing wrong with a couple of grown men playing with the children's toys there.
No, as a matter of fact, I received this from my PhD student from Japan. This is a very low entropy situation.
That's because it's highly ordered, is it?
It's highly ordered.
All the blue on one side, orange on the other.
That's right. And now, you can imagine that if this gets jostled around a little bit, like if I jostle it around, it starts to get a little bit mixed up.
Okay, so its entropy now is slightly higher than before, still relatively low though.
That's right. Shake it up, shake it up, shake it up, shake it up, shake it up. Whoa, we're starting to get higher entropy. It's getting more and more mixed. Troop, 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 troop. And we're pretty close to equilibrium here. Shake it, shake it. Looks the same.
In the Big Bang beginning of our universe, matter was evenly spread and highly ordered. So it had low entropy. Then the force of gravity did the shaking, pushing up entropy and creating galaxies, black holes, stars, planets and life.
In about 5 billion years, the hydrogen will run out in the sun. It will turn into a white dwarf, and then it will slowly sink in towards the center of the galaxy. It'll probably merge with the giant black hole there. The black hole will sit around for, 10 or 100 trillion years, and then it will evaporate. And eventually, the evaporating black hole will turn into photons everywhere, and nothing will happen after that.
The cosmos will then be just a sea of nothing but photons, maximum entropy. Our finite resource of order completely used up. The disturbing discovery Charlie's team's made is a lot more of that finite resource has been plundered than previously thought. And to work that out, he tallied up all the entropy in the universe. Turns out, that's not as hard as you might think. There's just one type of main contributor. It's at the centre of every galaxy. They're giant black holes, millions of times heavier than your stock standard hole. They contribute enormous entropy, as Charlie likes to demonstrate on the pool table.
Whoa,
hey, there we go.
You got
So
a yellow, you're
Smalls,
solid.
am I?
You're solid. $1 says you don't make it.
You're on.
Oh, yeah. Yeah! Oh, yeah.
Ah, you can't tell me you were trying to do that. To understand why black holes have high entropy, you need to think of entropy slightly differently, in terms of specialness. This lineup of balls is special because there are very few ways of doing it. It has low entropy. This arrangement, though, is high entropy. There's nothing special about it.
Matter of fact, if you go like this a few times, you can't tell the difference.
You can't
Look
do
at
that. We've got money on this game.
Look at this. See, it's equilibrium state. No matter what I do, they don't get any more messed up because they're everywhere.
This state is so unspecial, you can mess the balls up and it looks the same. Another example is a bedroom.
Check it out.
The teenager's room is really just messy, messy, messy. And there are many, many ways to be messy. You can know this by, if you go into the room, mess it up some more, it looks the same. So you can't get any messier. So there are many, many, many ways to be messy. However, if you go into that teenager's room, clean it up, then there are only very few ways to keep neat.
So, high entropy, low entropy. High entropy, low entropy.
Black holes are high entropy objects, and they're high entropy objects because we don't know what went into making them. You take any type of material and put it into a black hole, it makes a black hole of a certain mass. And I can take millions of Graham Phillips and make a black hole out of you. I can take that building behind me and millions of them and make a black hole. And those two black holes, if they have the same mass, are indistinguishable. Anytime there are many, many different ways of having the same structure, then that is a high entropy situation.
The researchers tallied up the entropy of all the giant black holes in the universe and came up with a number.
There is at least 10, probably more like 30 times more entropy in the universe than was previously thought.
So if you think of the path between the Big Bang and the end of the universe as a journey, we're at least 10 times further along that journey than previously thought. Cosmic life is indeed short.